All right, how's it going, everybody? We are here on Thursday, February 18th. We're going to talk a little bit of section 7.2 today. We're going to get a little bit more on our inverse trig functions here. In the last class, in our last video on section 7.1, we introduced our inverse trig functions, and we saw they kind of had some technicalities that we really need to be careful of, particularly their domains and ranges. What are the acceptable inputs and outputs that are associated with our inverse trig functions? So to get started today, we want to remind ourselves of what those technicalities are so that we can keep our eye on them all day again today. And today we'll look at some slightly more complicated situations involving mixing and matching which trig functions we are composing with one another. So our first example here is our cosine inverse of -1/2. So this is asking me the question. I took the cosine of some angle and I got as my output -1/2. What was the angle that I took the cosine of? The very important thing that I'm remembering for myself from our 7.1 discussion is that this cosine inverse function is only ever going to output values in the interval from 0 to pi, right? This was our acceptable output span for the cosine inverse. So this is saying to me, I am going to give as my answer, and again remembering, regular trig functions take in angles. Inverse trig functions therefore spit out angles. So I know that my answer is an angle, and I know that my answer is going to have to be in 0 to pi right here. This is mine. I guess I'm going to stick with this right here. This is my cosine inverse of x, and I'll call this theta right there, because we know we're getting angles that are coming out, right? So here's the thing that I'm thinking to myself. I'm asking myself, what angle did I take the cosine of if I got as an output -1/2? Well, I know that cosine is a measurement of the left-right location on the unit circle, so I'm picturing for myself that there really should be two different angles on the unit circle where we reach that location of -1/2, right? There's x equals -1/2 right there. And so it seems to me like there is one possible solution, but it doesn't live within our acceptable output span right there. On the other hand, it seems like we could be thinking about this angle right here, which would be within our acceptable output span. So what angle is that? Well, it looks like if we're only going to the 1/2 in the cosine direction, that's going to be like there's 30 degrees, that's right there, plus another 90 degrees. So I'm thinking 120 degrees, also known as going 1 pi thirds, 2 pi thirds right there. And notice that 2 pi thirds is, in fact, between 0 and pi. On the other hand, over here, this would be 3 pi thirds, 4 pi thirds. 4 pi thirds is not in our 0 to pi interval, so 4 pi thirds would not be an acceptable output from a cosine inverse function, despite the fact that cosine of 2 pi thirds is -1/2, and cosine of 4 pi thirds is also -1/2. We will never get this guy out because that 4 pi thirds is not within our acceptable span of values from 0 to pi, but 2 pi thirds is right there. So that's kind of our picture that we draw to kind of help ourselves out with this one. Other things that we saw in the last class was that our trig functions, whenever we compose a function and its inverse and we layer them together, what we're expecting to have happen is that they simply cancel. But the really important technicality is that we got to make sure, again, that we are staying respective to our appropriate spans of acceptable outputs from our inverse trig functions. I'm noticing here that I could do my sine function first, then apply the inverse sine function right here. So the inverse sine is the last thing that's happening. Therefore, I need to make sure that my output is appropriate for the outputs that we get from inverse sine. What I'm remembering for myself from the last class is that we selected the restricted domain of the sine function not from 0 to pi. That's what we picked for cosine, because this will get all the widths from +1 to -1. We wanted to get all the heights from +1 to -1 for the sine function. So for the sine function, we decided that -pi halves to +pi halves would be a good place to experience all possible outputs of sine one time. All the heights from -1 to +1 on the heights of the unit circle right there. So -pi halves, or sorry, yeah, -pi halves to +pi halves is our acceptable span of outputs. So my question to you is, I'm thinking that when I compose a function in its inverse, that we just spit out the original input right here, pi sixth, but that's only going to work if pi sixth is in fact in our span of acceptable outputs from sine inverse. I'm noticing that pi sixth is right here. That is exactly within our orange region right here. It's pi sixths. And therefore, we are just going to straight up get out pi sixths from this guy. It is the case that sine and sine inverse are going to directly cancel and leave us with the original input of pi sixth, because pi sixth is something I can get out from the sine inverse function. On the other hand, notice that 5 pi fourths is not within the negative pi halves to pi halves span. That's 1, 2, 3, 4, 5. 5 pi fourths is going to be this guy over here in the third quadrant. It is not one of our possible outputs from sine inverse. So in this case, we cannot just directly cancel our sine and our sine inverse. Let me say real quickly here. So we have to instead come up with an angle that is in negative pi halves to pi halves, that does have the same sine value as sine of 5 pi fourths. We want the information contained to be the same, but we have just got to be getting consistent results right here, right? So what we've got is we've got that 5 pi fourths is actually that like 45-degree angle right there. So my question is, what angle has the same sine value as 5 pi fourths? But is in the interval negative pi halves to pi halves. That's the question we're asking here. Since 5 pi fourths is not something that we can ever acceptably get out from the inverse sine function because it's not in the interval from negative pi halves to pi halves, what we have to ask ourselves is there a different angle that would give me the same output from sine of 5 pi fourths, but isn't that actual angle right there? And the thing that I'm seeing here is that since sine measures vertical height rather than horizontal width, what I am interested in is finding an angle over here. I'll change up some colors here so we can still see this. I am recognizing that there seems to be an angle over here that has the same height as 5 pi fourths, but is within our negative pi halves to pi halves right here. Now, negative pi halves to positive pi halves, I got to give a negative angle for the reference over here. So it seems like negative 5 pi fourths, or sorry, negative pi fourths seems to be my good answer right here. Negative pi fourths for that guy. That is the angle that has the same sine value as 5 pi fourths, but lives in our appropriate region of angles that are associated with the inverse sine function right there. Right? So these are the things that we did in our previous class here, and what we want to see today is that we can go even beyond this now by composing trig functions with different inverse trig functions, not just sine and sine inverse, cosine, cosine inverse, but maybe tangent and sine inverse, stuff like that. So let's go ahead and see what this is going to look like here. So two things. In last week's examples, each time we composed a trig function and its inverse, the inverse function was on the outside, right? Inverse function was on the outside, and therefore it was the last thing to be evaluated. Since it was the last thing to be evaluated, that was the thing where we said, what are the allowable outputs from this outermost function, sine inverse? And we said sine inverse is only ever going to give us out negative pi halves to positive pi halves, so we got to only give answers that look like that. Since pi 6 was in that interval, pi 6 was just our answer. Sine and sine inverse canceled. Since 5 pi fourths was not in the acceptable interval, we had to figure out a different angle that shared the same sine value, but was within the negative pi halves to pi halves interval. We came up with negative pi fourths for this guy here. All right? So now the two things that we want to consider today are, one, what happens if we put the trig function on the inside, right? Or put the inverse function, I think is what I want to say right there, put the inverse function on the inside instead of on the outside, right? Here the inverse is on the outside, inverse is on the outside. And two, what happens if we compose non-like functions? So let's take a look at our first example here, our sine of tangent inverse. So these two things are both happening, right? Notice that the inverse function is on the inside now, and we're composing non-like functions, sine with tangent inverse. So this is a weird expression, so let's talk about what is this even saying right here. Remember that regular trig functions, not inverses, regular trig functions take in angles and they spit out values. Therefore, inverse trig functions should be taking in values and they should be spitting out angles. So notice that tangent inverse is going to spit out an angle, and then that is the angle that is going to be the input into the sine function right here. So this makes sense. Kind of notice that it wouldn't really necessarily make sense if we did like sine inverse of tangent inverse, because then the tangent inverse would be giving us an angle, but then we'd be using an angle as an input into an inverse trig function. Angles should be outputs from inverse trig functions. So it kind of matters that we always compose a regular with an inverse there, right? So how would I verbally describe what we're asking when we look at sine of tangent inverse of 1/2? So by the way, same exact thing right there, just copied it down here. What we're saying is this. This tangent expression says, I took the tangent of some unknown angle, and I got an output of 1/2. I then want to take the sine of that unknown angle. What would I get, right? So this is saying we took the tangent of some angle and got 1/2. What would we get if we instead took the sine of that same angle? We're taking the sine of the angle that we got from taking the tangent of an angle and getting out 1/2. So I know what I got from applying tangent to an angle. This is asking what would you got if you applied sine to that same angle. This sounds like stuff that we actually did back in chapter 6, where we said, oh, given that sine of theta is equal to 1/2, find the other 5 trig functions. This is just a more complicated way of writing that same type of question right here. Another way that I could phrase this is, what is the sine of the angle that has a tangent value of 1/2, right? The output from tangent would be 1/2. The input into the inverse tangent is 1/2, right? So to find our answer here, let's just draw a triangle with the desired property. And here's the big algebraic thing that we're going to want to do in each of these cases. We know that outputs from inverse trig functions are angles. So I'm just going to call it that. I'm going to make up an angle, theta. That's our unknown angle, which, by the way, we'll never find in this problem because we don't need it. We need to find the sine of theta. I don't ever need to actually know theta, right? So I'm going to say that theta is tangent inverse of 1/2. I'm going to apply the tangent function to both sides. And notice the important thing that's happening here is that here our tangent inverse is on the inside. So particularly for tangent, I don't really have any concerns. Tangent as a function can output literally any value from negative to positive infinity. So it's certainly the case that tangent of theta can have as its output 1/2. There's no problems right there. So what I want to do is I want to draw the triangle that's associated with tangent of theta equals 1/2. And you should also notice that since I'm calling tangent inverse of 1/2 the angle theta, that means that what we're really looking for is just what is sine of theta, right? Tangent inverse of 1/2 is theta. I'm just calling it that. So our goal is just to compute sine of theta, knowing that tangent of theta is 1/2. So let's just draw a triangle that has these properties. I know that tangent of theta, tangent is always our opposite over adjacent. So let's draw a triangle with that property. In this case right here, relative to theta, you gotta draw your theta in there. We don't know what we're talking about. It seems like my opposite side should be 1, my adjacent side should be 2. I'm noticing here 1 squared plus 2 squared is 1 plus 4 is 5. So it looks like we're going to get the square root of 5 for our hypotenuse that's associated with this. Now I can say, now that I've built the triangle that describes all of my trig relationships relative to theta, I can now identify what we're going to get for sine of theta. Sine is opposite over hypotenuse, so it looks like we're going to get 1 over root 5. And it looks like that is going to therefore be my final answer for this guy. These, I think, in my opinion, are almost a little bit unbelievable right here. Not like, I don't know, not like unbelievable, but it's like, it'd be really nice if we could check these guys. So let's go ahead and pop over to Desmos real quick and check that. We were wondering, what is the sine of tangent inverse of 1/2? And what I really like about this, by the way, is that Desmos will never give you the exact answer, which means you can't just cheat and use Desmos because I'm always going to want the exact answer, not the decimal. But you can verify that you're right. We got 1 over square root of 5. And it looks like we're getting the exact same decimals here for these two, leading me to believe that we definitely nailed it right here. These two are clearly equal to each other. So feel pretty good about that one right there. So our guide with these is the triangle. Like drawing the triangle is going to be our biggest key for us today. And the other thing I think that's really important is to be able to see what this is even asking, right? This is saying I took the tangent of some angle and got a half. What would I have gotten if I took the sine of that angle instead, right? See this for like a whole question where we're being provided information and asking a related question as opposed to just a computation. This isn't just a thing you plug into your calculator. This is a question that's being asked that we can draw diagrams to represent the information that we're given. The information that we're given only involved the 1 and the 2. The triangle that we drew informed us that there should be a root 5 that's in association with this as well. Relative to the triangle, we were then able to identify the value of interest to ourselves, which is what we're calling sine of theta. And again, I think one of the biggest things that was like, I know that this is a thing that like I didn't like grasp when I first learned trig was any inverse trig function spits out angles. Regular trig functions take in angles. Inverse trig functions spit out angles. So tangent inverse of 1/2, the result of that computation is an angle. And so I just called it that. There's my angle. It's theta. So I rewrote sine of tangent inverse of 1/2 as just sine of theta. That's what we're really trying to compute, the sine of an angle. We wanted to compute the sine of an angle to get our answer. We didn't need to figure out what the angle was going to be. We did want to know what was the triangle that represents the associations with that angle of theta right there. So I said that theta was an angle, that's tangent of inverse of 1/2. I rewrote that as tangent of the angle is a half. That led me to my triangle. My triangle led me to the sine value. So kind of recognize that this is actually stuff that we did in chapter 6. We just didn't bring inverse trig functions into it. Now we see that we kind of have a small, simple, a small kind of complicated expression representing a bigger idea that we saw back there in chapter 6. So let's do a few more examples of these, see if we can kind of, get a little bit of a consistency with doing this right here. So cosine of sine inverse of negative 1/3 and tangent of cosine inverse of negative 4/7. Other things that you should notice, things like negative 1/3, things like negative 4/7, things like, okay, we had seen halves before out there. These aren't like angles that we are used to getting out, right? Those aren't values that we're used to getting out from trig functions right there. So if we were to solve for like what these angles are, it's not going to be like our 30s, our 45s, our 60s or anything that's nice like that. But again, you noticed in the previous example, we never had to find the angle. So again, I'm going to say to myself things like this is equal to, switch my colors back here, this is equal to cosine of theta, where theta equals sine inverse of negative 1/3. So I'm going to apply sine to both sides and just get that sine of theta must be negative 1/3. I know that this is my opposite over hypotenuse, so that should lead me to draw a triangle. Now, the negative on this one's one that we're going to have to be careful with, right? Notice that when I write negative 1/3, that could be negative 1/3, or it could be 1 over negative 3. But the point here is that since I'm trying to draw a triangle, I am recognizing that I can't have the hypotenuse length be negative because that's like our radius on our unit circle. It's a distance that's always positive. Our two legs one of those could be negative, right? If our triangle goes like this, it looks like I have a negative x value and a positive y value. Our legs can be positive or negative. Our diagonal, our hypotenuse, always going to be a positive number here. So I don't want that one right here. I think that this is a good way for me to think about where that negative belongs, right? So I'm going to go ahead and draw my relevant triangle here. It looks like we're going to have, relative to some angle theta, it looks like my opposite side needs to be -1. So I'm going to go ahead and draw my triangle reflecting that, right? There's my -1 for my opposite side right there. We've gone down by 1. 3 is my hypotenuse. And so I'm thinking here we should have whatever our x value is. I'll rewrite that in a second here. X squared plus -1 squared equals 3 squared. Well, x squared plus 1 equals 9. X squared is going to be 8. And so it looks like x should be the square root of 8 for our other angle, or other side length that we're looking at right here. Now with our drawn triangle, where we've incorporated the negative into the triangle appropriately, I can now say to myself, listen, what we are really interested in computing is what is cosine of this angle that we're calling theta. And so now from this, I can see that cosine of theta, cosine is adjacent over hypotenuse. Adjacent is √8. Hypotenuse is 3. So it seems like square root of 8 over 3 is exactly what we should be getting from this cosine of sine inverse of -1/3. I think we should go ahead and verify this over there in Desmos to make sure that we still kind of believe these things. Those negatives made that a little bit weird right there. Cosine of sine inverse of -1/3. Cosine of sine inverse of -1/3. And there's a decimal value. We got the square root of 8 over 3. Oh yeah, feeling good. Got the exact same decimals there. I'm very convinced that the exact answer that we got of √8 over 3 is exactly the same as the cosine of sine inverse of -1/3 right there. Very cool. Let's do another one right here, because I know that these are slightly weird to get used to right here, for sure. Tangent of cosine inverse of -4/7. So again, I'm going to say this is equal to tangent of theta, where theta is cosine inverse of 4/7. So I'll apply cosine to both sides. 4/7. Why did I write 4/3? 4/7 is definitely a thing that we can get out from the cosine function, so I don't have any concerns with like my domain range stuff right here. It seems like this is going to lead me then to draw my triangle. There's theta. Cosine is our adjacent over hypotenuse. So adjacent to theta is 4. Hypotenuse is 7. There should be some height, so I'll call it y temporarily here. It looks like 4 squared plus y squared equals 7 squared. That's 16 plus y squared equals 49. So y squared should be what? I subtract 16 from both sides to get 33, I believe. And so I'm going to get y. Notice here, it seems to me like, and by the way, it seems like there's actually a couple ways that this guy could have panned out right here. Notice that this kind of easily could have been a triangle like this instead. It does seem like we perhaps might need a little bit more information as to where these are going to live. Did I write this up here? No. But what I'm going to tell you is that what you are going to see is things like, if the angle that we were considering is known to be in the first quadrant, we'd get this positive y value for our answer. If it is known to be in the second quadrant, we can, and notice that's what I wrote right here, assume all angles are in the first quadrant. I think I'm going to write a little bit more associated with this one right here, just to kind of track this guy here. Notice that this 4 and this 7 did not indicate if this was going to be a first or a fourth quadrant angle, because notice the cosine value of either of these two is the same, right? Cosine is a measurement of horizontal distance right here on the unit circle, and those two are going to have the same x value, opposite y values. Right? So it seems like either of those is possible right there for that √33. So it seems like in this case right here, we are interested in identifying tangent of theta. So it seems like for tangent of theta, we should be getting, and by the way, notice here, it seems like we should be getting, in fact, I'm even going to get rid of that negative, even though it's technically correct relative to this one right here. We drew this guy right here with the angle theta just sitting right there. Here we go, this is what I'll do. So here, tangent of theta, well, opposite over adjacent, in that case, would be root 33 over 4. If we're in the first quadrant. Or tangent of theta looks like it would be negative root 33 over 4 if theta is in the fourth quadrant. So notice here that we don't necessarily have information that guides us towards that, with the exception of if I'm getting this cosine inverse, let's see here. All right, we did that cosine inverse in negative 1/2. I know that cosine inverse is always going to be giving me, didn't I? Oh, that's because we were taking the tangent of that guy right there. Okay. Well, in any event, let's go and verify that this root 33 over 4 is the numerical component of our answer. And if we knew what quadrant our angle was living in, then we could get that little bit more. And is that what I'm doing right here? Is that it's giving me the... I think that maybe my quadrant stuff. That's okay. Let's go look in Desmos for this guy right here. Tangent of cosine inverse of negative 4/7. I'm getting a negative 1.436 right here. And we're going to do our root 33 over 4. And it does look like we're getting that exact same numerical response right there. But it does look like this is suggesting to us that negative result right there. And I think that the reason that we're seeing that right here is because if we take the cosine inverse, this should be what angle gave us a cosine of negative 4/7. Remembering that cosine lives from 0 to pi, we should be seeing the one that's on the left-hand side over here. We should be seeing, if we got out negative 4/7, that should be giving us stuff that's on our left-hand side over here, in which case we're going to get inverse tangents that are, or tangent values that are going to be negative, because we'll have a negative cosine, but a positive sign right there. So that should be giving us that negative response that's right there. Cool. So a couple scenarios might crop up right here, but the point is that you're going to be given that extra information here. Now, the much more exciting ones, these are the ones that I like, these are the ones that are going to come up for you in your calculus classes next year here, is when we're applying these composite trig functions, trig function with an inverse function with a variable component on the inside, an x, or even other crazier things like x over x plus 3, stuff like that. So these ones are going to take a little bit more algebra for us right here, but we're still going to follow the exact same pattern of thought associated with these as we did with the previous. We just don't have a number to grasp onto right here. So I'm still going to do this same type of stuff where I'm going to say to myself, all right, I know that this is really just me looking for sine of theta, where theta is cosine inverse of x. So I'm going to apply cosine to both sides. But I know that I kind of want to think about this as like x over 1 because cosine is a ratio of two things. This should be my adjacent over hypotenuse here. Right? So I'm going to go ahead and draw my triangle. So relative to theta, adjacent should be x, hypotenuse should be 1. I'm going to call this y because it's a vertical height, and I want to know what is that vertical height right there. In a moment, I'd like sine of theta, and that should be our opposite over hypotenuse. So it should be, I need that value, right? So it looks like we're going to get x squared plus y squared equals 1, and I want to know what y is. So y squared equals 1 minus x squared. and I can take that square root here and get a square root of 1 minus x squared. And it seems to me that now I am able to say, therefore, sine of theta is going to be equal to, sine is opposite over hypotenuse, so it should just be square root of 1 minus x squared over 1, or just 1 minus x squared, 1 minus x squared. So same exact things happening right there, but we had to do this algebraically in terms of x rather than numerically with given lengths and measurements that are out there. All right? Let's do another example of this guy here. My best straight line ever. So tangent of sine inverse of x over x plus 3. Same thing, we're just going to have a little bit more algebra to deal with these guys right here. All right? So this is really saying this is equal to tangent of theta, where theta is equal to sine inverse of x over x plus 3. I'm going to apply sine to both sides. I'm recognizing this is actually nice because I know that sine is opposite over hypotenuse, so it seems like we've actually got a fraction already set up for us, right? So that leads me to draw a triangle here, but I'm going to have to do some work for this triangle here. Relative to theta, opposite is x, hypotenuse is x plus 3. What we want to know is what this side length right here, maybe I'll call it b for right now. Otherwise I would use x because it's a horizontal distance, but we've got x as our general variable instead. So what is b? Well, we should have b squared plus x squared equals x plus 3 squared. So notice it matters here that we can do a little bit of algebra. We need to be able to FOIL this guy out. X plus 3 squared is really x plus 3 times x plus 3. So I'll do 2 algebra steps right here. One, kind of helping out the people that are less comfortable with foiling here. So writing out x plus 3 squared as x plus 3 times x plus 3. Also subtracting x squared over to the other side. So I've got that guy right here. I know I'm going to take a square root, but I'll just wait on that for a second. This should be foiling. First times first is x squared. Outer is 3 times x. Inner is 3 times x. Last is 3 times 3 minus x squared. And what does it look like we're getting for b squared here? Well, it looks like x squared and x squared are going to cancel, positive and a negative. It looks like I have in total 6x plus 9. And so it looks like I now know what b is. B is going to be square root of 6x plus 9. And therefore, I can now state my final answer because now I have the entire triangle described. I am interested in identifying the quantity tangent. Tangent is opposite over adjacent. So it looks like I'm going to get x over square root of 6x plus 9 right there. Add some little notes in here. So we identified the entire triangle based on one of the known trig relationships, the sine relationship. We filled out the rest of the triangle so that we could determine the tangent relationship associated with theta right there. So I really like these, and these are ones that are going to come up big time when you guys are in your calculus class next semester, so these are pretty relevant right here. You'll for sure be seeing more of these, and especially in general in terms of x, rather than just in terms of a single number on the inside up there. But you should notice that literally every single problem I've done today, I've either drawn the unit circle or have drawn the relevant triangle. I can't do these without drawing the diagrams that are relating the quantities of interest for me. You should be drawing a circle or a triangle for literally every single one of these problems that you're doing. And they don't need to be artistic. They don't need to be finely measured. They need to have correct labels. That's the important stuff that we're looking at here. So one of the things that we haven't done so far is we haven't looked at inverse trig functions associated with our other trig functions, right? We've only done sine, cosine, tangent so far. So let's go ahead and see how we can kind of relate our other trig functions, our co-functions, our secant, cotangent, to the ideas that we are already familiar with associated with our sort of our our primary trig functions, right? So again, when I see an inverse trig function, the first thing I say to myself is, hey, listen, since regular trig functions take in angles, I know that inverse trig functions will spit out angles. So what I know right away is that it's cool for me to call this just theta, because I know that it's an angle, so I'm going to call it theta, right? So what I'm going to do is I'm going to go ahead and apply cosecant to both sides to get 2 equals cosecant of theta. Now I'm going to say to myself, well, what is cosecant really? Cosecant is really 1 over cosine, right? Or sorry, 1 over sine. I almost got it wrong right there. Remember, for these co-functions here, each partner pair, one of them has the co. Since there's a co on cosecant, there is not a co on its pair term. That's why I know it's sine right there. Now, what I think would be more helpful to me would be to solve this thing for sine, so I can just think in terms of sine, cosine, tangent instead of cosecant, secant, cotangent, right? So I'm going to multiply both sides by sine. And now I'll divide both sides by 2. And it looks like we're interested in sine of theta being equal to 1/2. So it seems to me like I could go ahead and apply a sine inverse to both sides here. And this is me asking, what angle did we take the sine of if we got an output of 1/2? That means that on the unit circle, I might as well just draw it right here. On the unit circle, we are interested in getting a height of positive 1/2. And I want to remember that there are more than one angle. There is more than one angle that'll do this for us. Because sine is measuring heights, we want to make sure that we're only giving outputs that represent the span of all possible heights once. So that's why I know it's from the bottom to the top rather than from the left to the right. What I'm recognizing here is that if I want to get an output of height 1/2, there are actually 2 angles that do that for us, but only one of them is in our span that we want. There's our one that's not in our span but does have a height of 1/2. Here's the one that is in our span that does have that height of 1/2. I'm remembering that 1/2 is smaller than root 3 over 2, and sine is measuring that vertical component. So I'm picturing our long x value but our short sine value. So this should be our 30 degrees or our pi sixths. We should go and verify this guy in Desmos real quick. We are wondering about the cosecant inverse of 2. If I pop over to Desmos, cosecant inverse of 2, and there's my decimal, and there's pi sixth, exactly matching the decimal that we're getting right there. So Desmos agrees with us right there with our answer of pi sixths. All right, our last one for the day right here. Let's look at our inverse cotangent right here. Cotangent inverse of 1/2. Again, inverse trig functions spit out angles. Regular trig functions take in angles. I know this is going to output some form of angle, so just call it an angle, theta. I'm going to go ahead and apply cotangent to both sides. But what I know is that cotangent is really the reciprocal of tangent. That's what we're getting for all of our other parts out there, right? So 1/2 is going to be equal to the 1 over the tangent of theta. And you should notice here that these, if we're getting 1 over 2 is equal to 1 over tangent, it better be the case that 2 is equal to tangent, right? And so what are we really getting for theta? Well, it looks like we're going to be getting theta equals, I don't know, was that helpful to us? So let me talk about why this is helpful and why this is not helpful. So this sort of just led us in a circle. I don't know an exact value for this. Just like I didn't know an exact value. cotangent inverse of a half, right? Both of those are unknown to me. So how did this help us? Well, the one way in which this really helped us is this. And this is a little artificial, but it's a thing. So here's the thing I'm thinking. My TI calculator has a tan inverse button, but does not have a cotangent inverse button. So the way in which this is practical is that if we are relying on our TI calculators to make these computations happen, and I know that my screen is flipped right now, but I know that you guys can just like look and be smart people here. What you should see is above the numpad right there is I've got sine, cosine, and tangent. And even more importantly, in blue above them is sine inverse, cosine inverse, and tangent inverse in blue. So we can press our second button to get to sine inverse, cosine inverse, and tangent inverse. So the point here is you don't have a cotangent inverse button on your calculator, but you do have a tangent inverse button on your calculator. So with this little bit of math right here that we did, we flipped our cotangent statement into being a tangent statement. This one I don't have a way to type into my TI calculator. This one I do have a way to type into my TI calculator. So that's a little bit of benefit that we've gained from this. Now on the other hand, if we're just using Desmos over here, we should see that I'm pretty sure Desmos is fine with cotangent inverse. So this is, again, a bit of an artificial gain for us right here. Right, so it looks like we are getting the same values for those guys right there. But again, only one of those is actually doable on your TI calculator. So that I should at least say that there is value in being able to re-express one trig function as another. That's still a thing that we're interested in always being able to do. And so I'll say here from Desmos or TI, I'll say cotangent inverse of 1/2 is equal to tangent inverse of 2 is approximately equal to, and what was the value that we just got right there? 1.107 if I'm rounding to 3 decimal places. And again, we just didn't know any exact values that were associated with this. We do know that we get out exactly 1/2 from some special angles associated with sine, so we got the exact right answer. We don't know any exact, we've never gotten 2 out from the tangent function yet this semester, and so that's a place where we can just go to technology and throw that guy into a calculator right there. So your kind of like big takeaway from today is, man, you got to be able to draw the triangle relevant to the situation. Whenever we see these composition of trig functions out here, especially when we have this inverse function on the inside, your job is to create the variable for the angle. Notice that never, like literally the word, or the character theta was never typed out in this entire document here. The letter theta never once showed up. I introduced theta as the person doing the problem in every single problem. You need to be able to say things to yourself like, outputs from inverse trig functions are angles, so name it an angle. Name it theta, so that you can play around with it, because now theta is something that you can take the tangent of. It's something that you can draw a triangle where theta is an angle inside. So recognize that kind of the big key here is you need diagrams, and you don't know how to draw those diagrams unless you have created your own variable of theta that is an output from an inverse trig function. That is your job to just, and it's a simple statement. Every single time I just said theta equals some inverse trig function. Theta equals inverse trig function, theta equals inverse trig function. Theta equals inverse trig functions happening down here, right? All those good things. Every time I just said, whatever the inverse trig function is, call it theta right there. That will then get me going. It's gonna give me something to write. Then I can say things like then I can take the cosine on both sides, and then this allows me to write a triangle, because now I know that cosine of theta is some x. Remember, anytime you just get a straight up number, write it as a ratio, so you can think of this as like adjacent over hypotenuse, those kind of things like that. So every single problem that you do for this homework assignment, you should be drawing a little triangle or drawing a little unit circle, depending on the context that you want to do it. The diagrams are so important here. Don't short yourself on those. The practice of the drawing the diagram is what's going to allow you to be able to do that diagramming in your head once you've done a massive amount of these eventually at some time on down the road. So there's the rest of our inverse trig functions. Where we're going after this, section 7.3, we're going to hit our trig identities. What we want to start doing is identifying more of these relationships. Things like sine squared plus cosine squared equals 1. That's a really special relationship relating to trig functions of a given angle. Turns out there's a whole bunch more relationships that are vaguely like that, and we want to identify all those and see if we can kind of work with them. So coming up in 7.3, we're going to introduce trig identities. We're going to be proving that two trig quantities are equal to each other that are not currently expressed the same as each other. So writing short proofs is going to be one of the things that we've got coming up. So in 7.3, we're going to introduce identities and proofs. 7.4, 7.5, 7.6 are going to be 3 sections on us just getting a bunch more trig identities that are going to help us exactly calculate a bunch more trig quantities of things of interest. So we're going to get things like, as of right now, we can only do like our sines, cosines, tangents of like our 30s, our 45s, and our 60s, and our 90s. Well, we're also going to get things like, how do we compute the exact value for sine of 15? Or even better, sine of 7.5. We're going to get an exact answer for that, not a decimal calculation for that, by identifying some more identities that relate trig quantities to one another. So those are what's coming up for our next 3 sections. After we do that, 7.3, 7.4, 7.5, 7.6, and 7.7 are solving trig equations. We did a little smidge of that in section 7.1 as sort of like my teaser, because I know that you guys just cannot wait. But we'll see those. It'll be 2 sections at the end of chapter 7 that will be on solving trigonometric equations. So we're still just dealing with expressions today. We still just have an expression, a trig expression. The very end of this chapter will group all this stuff together. Inverse trig functions, identities, to help us solve trig equations, which is really kind of our big goal here in chapter 7. So that's going to wrap it up for me here today. I will see you guys in our next video. We're going to talk trig identities, and that's an important one. We got to learn some kind of rules about our trig proofs and stuff like that. So that video I think is going to be very helpful, because these are things that people are generally a little bit less comfortable with. So I'll see you guys in the next video. Have a good one.